Okay. So, in this lecture today, we pick up from where we left in the last lecture. In the last lecture, we were talking about this sequence charts and how we can associate timing along with the sequence charts, which are part of UML. Okay. Now, it has got a number of limitations also, because many things are not expressed in this. Next, we come to a very important representation, which all of you know, that is finite state machines. Okay. And you know, finite state machine, we come to the next state. The next, we have got an input, a clock and an output, and the system is in a particular state Z, say, and the next state is determined by the input and the state in which it is in. All right. So, there are two functions. There are two functions. Say one is the let me call it the state change function, delta, the state, say Z is the present state, and some input x is the input. Here you can see x is the input, and it is taking it to some other state Z. And there is an output function, let us call it tau. The output function is giving us some y, and that y can be based on the state and the input can come to y, or purely from the state we can come to y. All right. So, based on that, we have got two different types of automata, which are Mealy and Moore automata. Right. These are this you might be knowing that in the Mealy automata, the output function is defined by output is dependent on the present state as well as the input, whereas the Moore automata it is only dependent on the state. So far so fine. So, that is an FSM, and we have seen FSMs all through your courses of study in computer science. Now, this CFSM stands for communicating finite state machines, when more than one finite state machines can communicate among each other. And how can they communicate among each other? By, we have seen there are means of shared memory, message passing, that sort of things. So, with that FSM, let us start to look at some specification with the FSM in mind. Look at this, read this left hand side, where we are trying to describe an elevator, and you are going to design an elevator controller. That is your objective. So, it is written that if the elevator is stationed at a floor, some floor, and the floor requested is the same as the present floor, then the elevator remains idle. Fine. If the elevator is stationed at a floor and the floor requested is less than the current floor, then the elevator will go down to the floor requested. If the elevator is stationed at a floor and the floor requested is greater than the current floor, then the elevator should go up to the requested floor. So, that is clearly that is written, but it is not possible for a machine or an automatic design system to understand this. That is one point. But there are some other issues here. We are not mentioning anything about the timing, the speed, that apart. Also, if at the same time both of them, from some floor you request the higher floor and some floor you request the lower floor, what will happen? All those things are not enumerated here. The same thing can be described in the form of a code, all right, a code, simple code, it is a loop, a continuous loop. If the required floor is the same as the current floor, then direction is idle, no direction. Else if request floor is less than current floor, then direction is down. Otherwise, if requested floor is greater than the current floor, then direction is up, end if, end loop. So, there are two commands, either go up, go down or idle, three situations. Now, this thing you have to understand, and the same thing I can put in more information if I just draw it in the form of a finite state machine. Let us try to look at this finite state machine a little bit. There are 3 states: idle, either the controller is in 3 states, either it is idle, the elevator is not moving up or down, or it is moving up or it is moving down. Now, when will it be in which state? If it is in idle and the requested floor is, if the current requested floor is less than the current floor, lower than the current floor, then the direction is down. Now, you look at this particular hash here. So, what are the things that we are showing in this diagram? One is that I am in a particular state. For example, I am in idle state, and the transition has got some condition here. What is the condition? The condition is that the requested floor is less than the current floor. On that condition, this is an action. The direction is down, that is an action. All right. So, some control signal goes. Now, do not confuse with this down written in small letters and this down, because this down is a state. The control signal goes that the direction should be down, and the state is that it is moving down. Okay. So, this is a very important part of any FSM transition, and this is an event or a condition which must be satisfied. All right. We will see later that we can also have state machines which have got some state S0, and I am moving to another state S1, and there is some event E and some guard conditions like this, followed by the action. Here, the meaning of this is that if the system is in state S0 and an event E occurs, this transition will take place only if this condition C is true. If this condition does not hold, even if the event E occurs, this transition will not take place, and consequently, this action A will also not be taken. All right. So, this C is called the guard or the guard condition. Okay. Now, going back to our elevator example. So, it was in state down, all right, and then what can happen? At assuming that there is a synchronous clock, it is checking that the request floor is still less than the current floor. So, it is going down. If the request floor is the same as the current floor, that means it has reached the desired floor, then it will come to idle. Okay, direction will be idle. Sorry, the state will be idle. All right. Now, again from idle, if the requested floor is higher than the current floor, it will start going up, and the same thing continues. So, here from you can see that from up, the system was in a state of moving up, and the requested floor is less than the current floor, then the direction is moving down. Now, you see this scenario that while it is moving up, if a request comes for a lower floor, then whether you will put the direction to down or not. Now, there is no condition here. So, it is a point that it is moving up, right. The state of the controller is up. At that time, I get a request of a floor that is lower, as this FSM is saying, it will start moving down. Okay. These specifics were not specified all over here, because this was purely sequential, right. Now, the merits of FSM are that it represents the system's temporal behavior very explicitly, no issue with that. It is suitable for control dominated systems. Demerits are because it goes by the events that take place. Demerits are there is lack of hierarchy and concurrency. As I go on moving for a complex, relatively complex system, the number of states will explode and the number of edges will also explode. So, it becomes very difficult for the designer to really get a feel of what is being intended and what is going on. All right. Now, I come to another model, a little bit of extension of finite state machine or automata. We are calling that timed automata. All right. Timed automata is FSM plus we are capturing the models of time, right. So, here is an example taken from the copyright is Peter Marvidals for this. We are starting, this is an example of an answering machine, telephone answering machine, all right. We start and the ring starts. Okay. Now, when this ring starts, x is a variable that is denoting time, and whenever the event starts, this x is reset. So, here x is 0 and the clock is ticking. So, setting x 0, so that is just like an action on the event ring, I come to wait state. All right. Now, in this wait states, I am here, it will remain in this wait state as long as 5 units have not elapsed. Okay. If 5 units have, within 5 units, an event can take place. That means, so I am giving that time, right. The person picks up the phone, lift off, talks, returns the handset, dead, fine. If the person does not lift off, then as 4 units of time elapses, as soon as 4 units of time elapses, it starts playing a text. The answering machine will play a text. Mr. So and so, I am sorry, I am not at home right now. You have reached Mr. So and so, I am not at home right now. Please leave a message after the beep, etc., etc. So, it plays a text, and then you see another time, another clock is set to 0. As soon as the end of text is given, then a beep is there, and that beep is there for some duration, and then I start, it has already become, at that time I start recording, and when I record, I again set this clock x to 0, and the recording time length can be up to 9 units, whatever that is. Now, that after that 9 units, I can go silent with a beep, or if the person has not been silent, then I will give a, the time has elapsed, I will give a beep and it will be dead. So, along with this, we can put in time as a variable along with FSM, that is timed automata. That is another way. There are different other ways also. of representing time and capturing the temporal behavior of this of embedded systems, but here there is one example that we are showing. Next, I come to a very important concept, that is of state chart. Now, state chart, why is state chart required? State chart is required because it will provide us with the facilities of abstraction, of hierarchy and concurrence both. Now, one major problem that we have already stated in terms of the finite state machines is that as the number of states go on increasing, the thing becomes incomprehensible. On the other hand, if I represent a finite state machine like this, as is being shown here, all right. This is a finite state machine with 1, 2, 3, 4, 5 states, and there are so many edges coming out from A to B on event G, from B to C on event H, like that. And from any state, if event K occurs, I will come to another particular state Z. All right. Forget about this part right now. So, and from Z, we can come back to M. So, consequently, there are number of states, and if the system becomes more complex, there will be larger number of states and larger number of transitions. One thing to note is that the FSM will be at any point of time will be in exactly one of the states. It cannot be simultaneously in more than one state. Okay. Now, you see that we can employ a hierarchy over here. We can say that this is one state, this whole thing is a state, and Z is another state. We are now abstracting out and giving less details. We are giving more details in phases. So, I first say that I have got two states here. What are the states? S and Z. And what happens? If event K occurs, then I exit from state S and come to state Z. If event M occurs, then I leave the state Z and go to state A. All right. Now, here we are having certain things to be noted, that as I said that at any point of time it will be either in either of these states. If the system remains in either of these states, then it is in this state, right? In either of these states, in A or B or C or D or E, okay, then it is in state S. So, these states are the OR states. Okay. Now, this is known as, this S is known as a super state, and these ones A, B, C, D, E are known as substates. Now, while in a super state, the system can be in any one of the substates. All right. Now, what is a current state? A current state is, if it is in A, B, C, D, anywhere, then it is in a current state. Then that, or anyone. So, for example, it is now the machine is in D, then that is in the current state or the active state. Okay. And also this whole thing is a current superstate. Okay. So, I have got superstates and substates, and I have got this OR states. Now, there is another thing called the default state or entry state. Whenever I am entering S, now S comprises of 5 substates. Now, if here I am showing explicitly that if event M occurs, it goes in to particularly to the state A. It is possible that on some other event, say K, K was already here, no, K is here. So, some other event may be L, it enters here, I show it here. What does this arrow mean? This arrow means that it goes to this superstate, but I have not specified where in this superstate it goes in. For that, we usually denote the a default state, for example, like this, a solid circle with an arrow. That means, whenever this means, what does this mean? This means whenever S is entered, unless specified otherwise, enter A. Okay. So, this is known as, then A is the default state or the entry state. All right. Clear? All right. So, here you please distinguish between these two, that I can enter and specify directly that I will go back to this state or this state or this state, or I can simply come to the superstate entry point and say that I am entering somewhere in the superstate. I am not interested in specifying that. The responsibility of specifying which is the superstate of S is up to the person who is designing this part. So, thereby we can modularize the tasks also, right. Now, we come to another point, that is a history mechanism. Okay. Let us leave aside this and try to concentrate on this part. The same state chart is being shown here, and here let us look at this. What does this signify? This signifies that it is when S is entered, A is being started, then on event I am going on like this, as my pen is moving, I am going on like this, okay. And at some point of time an event K occurs. An event K occurs, right. As the event K occurs, I come out of Z, come out to Z. Now, do you know that when event K occurred, where was I? I could have been, what does event K tell you? Event K tells you that you are coming out from state S, right. You are coming out of state S, but you do not know which substate you are coming out from. So, if I draw like this, that on event M, it goes to a node H. H is nothing but a history node, as if it is keeping a record of the different states through which the machine is traversing. I am remembering that. So, if I specify in this way that on M, while I am in Z, I will be going to the H node. What does that signify? That I will re-enter S through the state from where I left. Suppose I left from here. Actually, when K happened, I was here, right. Then H will actually take me back to this state C, from where I will continue. Clear? I repeat, suppose I came out, I am specifying that wherever you are here, on K you are coming out to state Z, and on M you are re-entering state S. Okay, you are re-entering state S. Now, suppose, what does it signify? Now, when you actually K occurred, suppose you were in state C. So, you came out. Now, this H node will remember from where you came out, where you were at the last point of execution. So, when this specification tells me that, well, you go back to S and follow your history node to find where you were, then this history node tells me, well, I know I was in C. So, when I enter this, I will not again start with A, I will start with C. Clear? That is the role of the history node. Now, can we combine this history node and this default entry node? Now, here, as this diagram shows you that the history and the default can be combined in this way, that when I enter M, I will go to S. I will enter S and I will go to the default node. The default node will check the history node. If the history node does not tell of any other node from where I exited, if the history is empty, then I will come to A, to my default node. Otherwise, this will direct me to this node. You see, state chart is a graphical language. So, whatever we are stating here are all stated through graphical diagrams, which are taken by a compiler and converted to some executable form. All right. But when you are drawing this, your drawing must have a unique meaning. The semantics must be unambiguous. That is why these meanings must be made very clear. Okay. Now, we will come to, so we have seen the hierarchy and how the hierarchy can be maintained. Next, we come to the issue of concurrency. Again, we are taking the example of an answering machine, and let us try to understand this answering machine. I assume that all of you have got some idea about what an answering machine is. An answering machine is connected to a telephone. As the phone comes in, either you pick up, or after some time the control goes to the answering machine and the answering machine answers you, etc. Now, that thing should be irrespective of my explanation. When I am specifying an answering machine, the behavior of the machine should be clear from this diagram. What is being shown here? Again, look at the superstates and substates. This is the super-state, which is the answering machine as a whole. Now, this answering machine can be in on state or can be in off state. Okay? In on state or off state. Now, from off state, if now when the system enters, by default in this block, entire block, here is the default entry node, it comes to the off state. When I put the key on, it goes to the on state, right. So, off and on, are these the AND states or states? These are OR states, because I am either in the off state or in the on state. When I entered the on state, because I have put the key on, then this is the behavior. This behavior comprises of two other states which are separated by this dotted line. This dotted line means that this state and this state are concurrent. They are not sequential, both of them are going on simultaneously. All right. What are these states? This state is a line monitoring state, where I am checking the line whether some call is coming or not. And here is a key monitoring state, where excluding on and off, because on and off are being done with this switch, on main on and off switch. Besides that, these are telephone keys or something. Now, let us see. So, it will be when I enter key on, when this transition key on takes place, I enter this on state. Where do I enter the on state? I enter in both. So, both of them have got their default state specified. For the line monitoring state, I am entering in the substate L wait. Now, you see line monitoring and key monitoring at the hierarchical at a higher level. If I decompose them further, then I get the states like line wait and line process, key wait and key process, these things, right. So, I entered this line monitoring through the line wait, I entered the key monitoring through key wait. Now, the next level of hierarchy tells me what is the behavior of line monitoring and what is the behavior of key monitoring. Line monitoring, it waits till the event ringing of the phone occurs. Ringing is occurring, then you process the line. What you do, I am not specifying at this point of time. I can specify at a lower level of hierarchy, where I can say connect to the phone, raise the receiver, talk, etc., etc. That was shown there. But all those details I am hiding. That's why the abstraction is so beautifully captured in state charts. And from line process, whatever might be the details of the line process, when I hang up, the caller hangs up, then I go back to the line wait, or I keep the phone down, I will also go to the line wait. Now, in the key monitoring, I am waiting for the key to take place. I am waiting for some key pressing, and as the key is pressed, I go to the key process. Key processing, and when the key processing is done, I go to the key wait. Now, what are the typical key processing activities? We have seen in an earlier lecture with an answering the UML, before that UML we are showing some use cases that the keys can be record message, read message, delete message, all those things, right. So, that is hidden inside this block, whatever processing I am doing. Okay. So, this is the top level. Now, this is known as AND superstate. Why is this known as the AND superstate? It is known as the AND superstate because when I enter ON state, I am simultaneously in line monitoring and in key monitoring, both of them are active. So, the FSM is in all immediate substates of the superstate. It may be that it is in L wait, it is in K wait, fine. Say, look at my fingers, I am right now in L wait and in K wait, but that means I am in line monitoring as well as in key monitoring, both of them. If I am in line L wait and I am doing some key processing, no phone has come, but I am just recording my messages or whatever, then also I am in line monitoring as well as in key monitoring, right. In this big picture, line monitoring and key monitoring, I am within that, both of them I am in, so that is active. If I am doing line processing and I am in key wait, then also both of these are active. So, it is in all superstates, I mean substates of the superstate. This is superstate. In these, that is why it is called AND superstate. Okay. Now, how can I do some, I mean entering and leaving this? Say for example, from key processing, I do somehow I was here, all right, I was in K proc, and then I have pressed the key off. I press that, then that will immediately bring me to this off state. Okay. And when I press key on, it will take me to the key processing state. Very good. So, when I do key on, when I, as has been pointed out, since history is not there, I am not being able to, I do not really know where I should go. Therefore, I should simply enter key on, I should go here, right. So, I need not, I could go here provided there was a history node. If there was a history node, I could have gone here. Since the history node is not there, I cannot go in there. I will take this path, all right. I will take this path. So, on key off, I am coming over here. So, entering and leaving the AND superstate. So, whenever I put the key off, I am coming to off. That means I am exiting what? What am I exiting? I am exiting the on superstate. As I am coming out, as the arrow shows, I am coming out of course, key processing substate, but at the same time I am exiting this superstate altogether. And when I am, so then my line wait also goes, right. So, I can further go in on key on and I can start from here and here, all right. So, so much for now. We will have to continue with this state chart. There are some more things that we have to discuss that we will do in the next lecture.